Heyo, it's me, 8-Bit Games here, back at it again. My computer broke, so we're stuck in this incandescent void again. Anyways, we have some new spell pieces to check out. Today we're going to be going over Entity Raycast, Vector Sum, Sine Function, and the Cosine Function, and Particle Trail. To get us started, we're going to go to Entity Raycast. Now, it's a lot similar to a previous spell piece we've gone over, Vector Raycast, where you take a position and a ray, and it makes a line there and checks what entities it hits, or what blocks it hits. Difference is Raycast just does blocks, while Entity Raycast does just entities. So, little demonstration here. We're going to choose a position. We're going to do, position. We're going to do position of the caster. So entity position on the caster. We'll give our position. And we're going to use that as the position of our line. And then we're going to make it go into the direction that we're looking at. Entity look will give the direction we're looking at as a vector, and then Raycast can use that for whatever it wants. Then we're going to do trick debug so we can see the output. Boom. One wrong spell. Boom. Now, I want to note this because it's an important thing. So it made a line to see everything the first thing it hit in that line. Where did we put the line? In our position. Entity position returns your position. So the line starts inside of you. So if we want this to not start inside us and start somewhere else so we can get entities, we need to alter our position vector, which we can do with vector sum. Vector sum is pretty straightforward. It just takes two vectors and adds them together. Like, look at this. If I can add my look direction onto my position vector, and this will cause it to return a vector that's a combination of the two. So my look vector has a magnitude of 1. So it took my position and moved one block in the direction I was looking, which we can see here by noting the difference. So pretty useful. If you want to know how the math of this works, you just take the x value of the first vector, then add it to the x value, the second vector, and that becomes your new x value, and same with the y and z axis. So there's that. But back to Entity Raycast. Now that we can move our vectors onto another vector we've chosen, let's get rid of this entity position and return a new position that's going to be a combination of where we're looking onto our position, which will fix this spell and make it so that it returns any entity we look at. Boom. Yeah. So, just a couple of things to note there, besides the spell pieces, is that, make sure you don't put the line inside your position. I'll put the stats for what examples of the inputs and outputs look like, but this is our 5th episode in the series. I think you should have some idea of what a unit vector and a regular vector is difference wise. And if you don't, check out my, I think it's 3rd video I covered that. That'll help catch you up on that. It's very important to know. Okay. Now that we have entity raycast and vector sum, what can we do with this? Well, we can make a line that will detect any entity that goes into it. So that means we can then do things on those entities, like do a trick that regenerates the entity, or do a trick that gets that entity's position and then causes lightning to come down on it. Unlimited. Oh shoot! I forgot that they turn into piglins. I was gonna make a Star Wars joke. Alright, well, yeah, so there's a prime example of that. So, yeah, that was an example of a vector sum and entity raycast. Now that we have a practical understanding of how they work, let's go into Desmos for a more visual understanding of how it works mathematically. Alright, we are in Desmos, and I'm going to show you what vector sum looks like. Now, as you know, we have two vectors represented by points x and y. And these sort of make a line, with the magnitude being the length of that line. So we could have a vector of direction 1, 1 with magnitude of 2, which would be out here. Now, if we wanted to add these vectors mathematically, we would do x1 plus x2 and y1 plus y2. But what does that look like? Well, if we combine the two, it would look like this. Now, this might seem like, a bit odd, but if we take 0, 1 and add it to 0.5, negative 0.5, 0 plus negative 0.5, negative 0.5, and 0.5 plus 1 is equal to 1.5. So they match up. And this looks even more closely because if we just place our second vector onto the first one, then where they go to is equal to their vector sum, which you can see here. So that's essentially what vector sum looks like and how to do it mathematically. Let's head back to Minecraft and see some more spell pieces. Now, next part. This is going to be a bit complicated. I mean, well, that was linear algebra, vectors and all that, and this is trigonometry. So reasonably, it's less complicated. But the sine and cosine function, they look like every other function where they give an input and they give an output. However, if we do loop cast index and we get ourselves a loop cast bullet, you're gonna see something pretty debug. Yeah, okay. I forgot you can't make a spell unless it's a trick. You're gonna see a weird pattern, in my opinion. So if we debug the output of a sine function, as you can see, it goes from 0, then goes up to 1, then goes back to 0, and then it goes to 1, and so forth. Then negative, well, it goes 0, 1, 0, negative 1, 0, 1, 0, negative 1. It's constantly going up and down in a wave function. Where it's like up and then down, and then up and then down. Kind of like the waves on a beach. Cosine is exactly the same, except those difference is that it's going to start at 1 and then go to 0, and then negative 1, and then 0, 1, negative 1, 0, 1, negative 1. Which will start out like, which will start up, then down, and goes back up, and down. And that might look the same, but they're quite different. And you might be wondering, 8-bit, what's the importance of this? Well, we're going to use it for JJK and style spell called simple domain. And let's get out of Minecraft and go to Desmos so I can give you a better example. Okay, here we are in Desmos. We have our sine and cosine functions. And as you can see here, at 0, it's at 1 for cosine, and at 0, it's at 0 for sine. And if you'll notice, they both kind of intersect the line or reach the maximum and peak at the same point. When one's at the x-axis, the other is either at minimum or maximum. And it keeps going like this in this weird wave pattern. Well, what this represents is kind of like a circle. You see how it fits a bit. At the start of the circle, assuming we start right here, you would be at position 0, 1, which is what these functions do. They describe, well, for cosine, it describes the x length of that part of the circle's edge you're at, and for the sine function, it represents the y length of that part of the circle. And the thing about sine and cos function is we can use this for any circle, not just a unit circle with radius 1. We can do it because the length of the circle, its outside, has this unique ratio with its radius. For every 1 unit of radius, we have a 2 pi unit amount for its arc length. So this is the length of the outside of this circle is 2 pi. If we want to increase radius by 2, its outside part would be 4 pi, and so forth. Yeah, and right here is a better demonstration of sine and cosine, with the blue being cosine and sine being the y-axis. And this th is radians. Radians are kind of like degrees, but it's more of like the amount of the portion of the outside of the circle we've traveled, starting from here. Alright, that seems a bit complicated. Let me explain. If this is 0, and moving around this entire thing is 2 pi, that means going 360 degrees around the circle is equivalent to 2 pi. If we went around half the circle, that means we went half of 2 pi, or pi. And if we went a fourth, that's pi 1/2. So we can use radians to represent how much of the circle we've traveled up. And that's what th represents. It's our radians, which will then give us the point that sine and cosine correlate to with that portion of the circle. So if we go to 0, it's at 1, 0. Then if we move to half pi, it's not perfect. It'll be 1, 0, 0, 1. Then we can move to pi, which will then flip, then go all the way to 2 pi. And we can keep going, which is why the sine and cosine waves go up and down, because as you just increase the radians past 2 pi, it just keeps making circles. Yeah. This is the representation. This is the sine function, this is cosine function. I kind of have the cosine function a bit upwards out here, so it aligns better with the cosine length, just to show you. But yeah, we'll start here, and then as they traverse, you can see it moves up the sine function and across the cosine function, and the 2 points at the same radians equals that point on the circle. So yeah, that's essentially, that's what cosine and sine represent. It's might be a bit of a hard concept, but it gives us something. We can make a unit vector using the 2 points of the cosine and sine function to point in whatever direction we want based off a radian input. And I will show you an example of that real quick. So let's get back to Minecraft and I'll get to it. Alright, now we know how vector sum and entity raycast work, and we've seen examples of it. We are now going to get into today's spell, which will be using particle trail to show us our vector as we make it so we can course correct. Particle trail is pretty neat because when you cast it, it chooses the position you want and the ray you want, so we can simulate any vector we'd use for a spell using particle trail. Now, with today's spell, Simple Domain, the idea is to recreate Simple Domain by JJK, essentially make a circle around the player and have it do whatever effect we want. Using our cos and sine equations, we can make a direction raycast dependent on, I don't know, the amount of times our spell is cast, in order to sort of like just make a line that we can scan in the shape of a circle to mimic a circle, because we can't make a circle inside, but this will get us pretty close. So we use loop cast index, which is like our x value. Remember our sine cosine functions. This will increase each time the spell successfully cast. We're going to times this by the radian. I chose pi 12 radians so that it's an accurate raycast, though a slow one, but it'll still fill the circle pretty well. And that will go into our cos and sine in order to constantly make a direction vector in the way of a circle that we can then put around us. Do note, I added the player's look vector to the cos and sine bit so that the spell doesn't make the vector collide with the player, because I intend to use entity raycast in order to make effects happen. But if it's in the player, then the player would get selected, and we don't want that. So we're just going to add our look vector to our direction vector to make it so that it doesn't collide. And as we run the spell, you can see it makes a circle around us. Now, it is a bit jittery, but that's because we're just making a line and passing it around like in the shape of a circle. So it's not completely accurate. But as you can see, it's hitting around the circle every pi 12 radians. And that does make our sort of simple domain shape. Well, now that we have the shape, how can we add an effect to this? Well, instead of using particle trail, we could instead be using entity raycast. Entity raycast is a bit like vector raycast, but instead of looking for blocks, it looks for the nearest entity that it hits. And so with that, we could then put a spell like ignite, and this will cause our simple domain to instead ignite entities around us. Did I upgrade this? Boom. There's an arrow because it will arrow when it doesn't run into anything. See, it's starting to ignite entities. Now it is slow because the sweep is a bit jittery, and it's also not hitting mobs below the eye line because we have the position of the Raycast at our eye line. So anything below that won't get hit. But if we crouch, we should then start hitting other entities. Now it does need some work, but this does do what we set out to do, makes a circle shape, and then applies an effect to the entities in that shape. Now we can change this to we could change this to summon smite to make it so that we then well, if we do entity position on the entity we get and then do smite, we can cause it to smite in a circle around us. Yeah, boom, see? It starts hitting things. Now, you could make the circle sweep faster by going to a shorter radius. As you notice, it doesn't get every mob around that. That's because it takes about 24 casts to go the entire circle distance. That's approximation for about 4 casts a second. That's 6 seconds in order for it to scan the full circle. So some mobs will get lost in that. You could make it faster by decreasing the radians from pi 12 to pi 4th. But that'll make the circle less accurate as it'll start skipping larger segments instead of taking larger time. So there's a bit of you know, whether you want to be more accurate or faster, or you could run 2 entity Raycasts at the same time and offset them by some radians around the circle, and that would make it more accurate, and you could make it faster. Yeah, but these are things that you might need to trade off for when making a spell. But yeah, so that was entity Raycast, vector sun, the sine and cosine functions, and a bit of an example of particle trail and our simple domain spell from JJK. I hope you liked the video. If you enjoyed, please like and subscribe, and have a great day. Be safe.